We are continuing on with our study of matter, and we started on a very tiny scale, individual subatomic particles, protons, electrons, and neutrons. We put those together to make atoms, and when we did that, we saw periodic trends and understood more. Then in more recent chapters, we put the atoms together to make molecules and ionic compounds, and we learned even more. Now we're going to scale up again to a real world scale. We're going to look at collections of molecules together to make solids, liquids, and gases. And this schematic here shows the difference between them. In a solid, the particles are locked rigidly in a regularly ordered crystal. But as we raise the temperature, the kinetic energy makes the particles move around more rapidly. And you can see in the liquid that although the particles are close together, they're not locked in place. They jiggle around. When we get all the way to the gas phase, there is so much kinetic energy that the particles are far apart from each other. They act completely independently of each other, at least to a first approximation. What we're going to focus on in this chapter are the liquids and the solids, which are called condensed states or condensed phases. The particles in liquids and solids are close enough together that they are attracting each other. They must attract each other because they won't fly away if we pull the stopper off those flasks. Now, if we understand the forces holding the particles close to each other in liquid and solid, we can predict even more properties of the material, and that's what chemistry is. Just a little joke. This came on a birthday card I got many years ago. You don't think it's funny? That's all right. I told you early on, I hope, that all of chemistry boils down to opposite charges attracting. And we looked at that more formally mid-semester in the form of Coulomb's law. We said that the force of attraction between charged particles was proportional to the charges and inversely proportional to the distance between the centers of charge. Distance between. We first utilized Coulomb's law when we were looking at attractions between electrons and nuclei within the atom. But now we're going to use it looking at attractions between one molecule and another molecule. So these are called intermolecular forces, and those are just attractive electrostatic forces. Between molecules and or ions. It's called intermolecular forces, but we're going to talk about ions here all at the same time. What it's going to boil down to is that the bigger the charges on the molecules or ions, the stronger the attractions. Coulomb's law says the bigger the charge, the bigger the attraction. And that means a stronger intermolecular force. IMF, for intermolecular force. Before we get too deep into this, I want to clarify the difference between intramolecular forces and intermolecular forces. In this chapter, we're focusing on intermolecular forces, the attractions between two different molecules. The way I remember that is that international competition is between different countries. Intermolecular forces are attractions between different molecules. Contrast with that is intramolecular force, and that means within the molecule. Just like intramural sports are within your school. Intramolecular forces are within a molecule. And we seldom call intramolecular forces that. We usually refer to those as covalent bonds. So the intermolecular forces we're going to look at are much, much weaker than the covalent bonds that hold molecules together. As we put energy into a compound, we can make it go from a solid to a liquid to a gas, but we absolutely will not put in enough energy doing that to break covalent bonds. They're way too strong. We're going to look at intermolecular forces because they determine the physical properties of a substance. So I've got an example here, and I'm going to have to explain this symbolism to you. This means an enthalpy change, which roughly speaking means heat. We'll study that in more depth first thing next semester. And the vape there means the heat of vaporization, which is just a fancy word for boiling. So it says to boil water, we're going to have to put in this much energy. To take liquid water and to turn it into gaseous water, we're going to have to put in that much energy. Now, that much energy by itself doesn't mean anything to you. That'll just be a reference to a later amount that I show you. Let me remind you that boiling something is a physical change. It changes the state, but it doesn't change the molecule. It's an H2O molecule in the liquid. It's an H2O molecule in the gas. So this is not a chemical change. It's a physical change. And the amount of heat that it takes to do that depends on the strength of the intermolecular forces. I have to pull one molecule further away from another one, overcoming some of those intermolecular forces to boil it. We're going to contrast that with the covalent bonds within the molecules, which determine the chemical properties. And as I said in the previous slide, those are much stronger. So this symbolism means the bond dissociation enthalpy, or energy, which is the energy to break the bonds. So what that energy is telling me, if I wanted to take a water molecule, and it's defined for the gas phase, not to worry about that, and break it into two hydrogen atoms and an oxygen atom, I would have to break two oxygen-hydrogen bonds, 2 times 463 kilojoules per mole, or a total of 926 kilojoules per mole. The only point in showing you that number is to see that it's many times greater than the energy to overcome an intermolecular force, an attraction between molecules. So when we do physical changes, we're going to use a moderate amount of energy to affect how close molecules are to each other. We are not going to break chemical bonds. No way. Now let me show you something. I got an ad that shows that not everybody knows that. One of the things I like to do is collect ads that show misuse of chemistry, bamboozling people. And this is an ad from a Land's End catalog. It sells outdoor clothing. They developed these new long johns, and I want to highlight in the next slide this graphic here. Somebody actually went to the trouble to draw water molecules here. Now, they made a little goof. They put a bond between the two hydrogens. That doesn't worry me so much as the other thing I'm about to show you. It says, water, also known as sweat, is attracted to thermoskins like ants to a picnic. Our constant comfort process separates the H2 from the O, making evaporation take place much faster. And they show that. There's the H2 separated from the O. No! When something evaporates, it doesn't break a covalent bond, and we're lucky that it doesn't. If that happened, H2 is a flammable gas. Oxygen atoms aren't stable by themselves. If you came in from the ski hill and that was happening to your sweaty long johns, you sit by the fire and you're going to blow up. Fortunately, not true. Now, part of the reason that ad has a pride of place in my collection is that in the later years, somebody figured out that they were wrong. So here's the updated one, and it says the differences in the detail. Now it talks about water being polar, that it has a slightly negative end and a slightly positive end. They show full charges. I'll forgive them for that. So it's just saying because of the polarity of water, it adheres to the fabric and not to your skin. That's true. Now, just as a little aside, it's not easy to visualize the difference between a chemical and a physical process in the macroscopic world. And it frustrates me that at the beginning of grade 11 chemistry courses, or Chem 50, they'll ask you to distinguish a physical change from a chemical change. I don't know how they can expect you to do that until you can see the process on a molecular level like this. I think they're just trying to get you used to being questioning about that. But now we're getting better and better at seeing the molecules. We're going to be able to identify physical and chemical changes better. So that was an introduction to what an intermolecular force is. Now we're going to look at different types of intermolecular forces. And I'm listing them here in order of decreasing strength. We're going to start with the strongest and go to the weakest. You don't have to memorize that though, because the attractions between particles follows Coulomb's law. The bigger the charge, the bigger the attraction. So I'll tell you the overview before we even get going. We're going to look at attractions between fully charged things, which will be stronger than the attractions between partially charged things, which will be stronger than the attractions between things with no charges at all. All right, here I go. The first intermolecular force I'm going to call an ion-ion interaction, and that means it's an attraction between one ion and another ion. Now, this textbook doesn't show an ion-ion interaction explicitly because it's synonymous with something they already told you. An ion-ion interaction is the same as an ionic bond, and if you want to call it that, I'm fine with that. Let me show you a particular example. My favorite ionic compound is sodium chloride, and now that you know something about atomic structure, you could figure out that the chlorides are bigger than the sodiums. But in an ionic compound, what you have is a network in which the negative chlorides attract the positive sodiums, and we get this crystalline network. Remember, those lines are imaginary. All that's holding this together is the electrostatic attraction between the positives and negatives. And because they are full charges on those ions, that gives me the strongest type of intermolecular force. Why do we care? Because these intermolecular forces are reflected in the physical properties that we observe. So as an example, I've looked up the melting point of salt, 801 degrees Celsius. That's very high. And that's because with the attraction between the fully charged ions, it would take a lot of energy to pull those ions apart from each other so that they can slide past each other in the liquid. You could also have different strength of ion-ion interactions for different ionic compounds. In the lab, you made magnesium oxide in experiment 1, and magnesium has a charge of +2 and the oxide's 2-. So that's even a larger charge than in sodium chloride, where they're only +1 and -1. The bigger the charge, the stronger the attraction in the ionic solid. The stronger the attraction, that's synonymous with saying a stronger intermolecular force. So we could predict that magnesium oxide would have an even higher melting point than sodium chloride. It takes even more energy to overcome the stronger attraction. And in experiment 1, where you made magnesium oxide, you didn't even worry about melting it, right? You used the heat from the crucible and the magnesium oxide didn't melt at all. All right, that was a full charge with a full charge. What can we look at next? The next kind of intermolecular force I'll look at is an ion-dipole interaction. And that's an attraction between an ion and a molecule that has a dipole, or in other words, a polar molecule. So now we've got an attraction between a fully charged ion and the partially charged end of a polar molecule. And we saw this in context before when we talked about water being a good solvent for ions. The positive ion is attracted to the negative end of the water. If there wasn't that kind of attraction, salt wouldn't dissolve in water. Next kind of interaction, dipole-dipole interactions. In other words, the attractions between one polar molecule and another polar molecule. Now I'm going to look at two parts to this. This A is going to be attraction between most polar molecules, but pay attention when I get to 3B to see how it looks a little different from this. Of course, what's the same all the time is that opposite charges attract. So if I have a polar molecule with one end a little bit negative and another end a little bit positive, then it's going to be attracted to another molecule. The negative of one end will approach the positive end of the other. And that attraction is the intermolecular force we call a dipole-dipole interaction. Now in general, these are weaker than the ion-ion and the ion-dipole because I now only have attractions between partially charged things. But within this broad class, dipole-dipole interaction, there's actually a continuum of strengths, just as there was for the two different ionic compounds I showed you earlier on. If the molecule is more polar, then the magnitude of the partial charge is greater, and the strength of the dipole interaction will be even greater. So that's 3A, partial charge attracting another partial charge to make a dipole-dipole interaction. 3B is a special kind of dipole-dipole interaction. It's still an attraction between one polar molecule and another polar molecule, so that's why I still have it in category 3. But it's especially strong. 3B is actually stronger than 3A. Now there's a name for this kind of interaction. It's called hydrogen bonding, and you may have heard of this in biology class. I'll explain to you in a second why I hate that name, but first let me tell you what people have agreed that it means. It's a dipole-dipole interaction between a molecule that has a hydrogen bonded to nitrogen, oxygen, or fluorine, and another nitrogen, oxygen, or fluorine atom in another molecule. And what's special about nitrogen, oxygen, and fluorine is that they are the most electronegative atoms. They're in the upper right-hand quarter of the periodic table. So let's see why that makes an especially strong hydrogen bond. My example here is HF. So I've got a hydrogen bonded to a fluorine in this molecule. Now, that's a polar bond. Fluorine has much greater electronegativity than hydrogen. So in that shared pair, the fluorine gets most of the electrons. That means that the hydrogen is essentially a naked little proton. A hydrogen atom had only one electron, and when it shares with the fluorine, and the fluorine pretty much steals it away, that leaves a naked little proton. So it's a pretty concentrated charge in a pretty small volume. Remember, it was the electrons that took up most of the space in the atom. I've got a really concentrated charge on this hydrogen. And what Coulomb's law says is the bigger the charge, the stronger the attraction to the other molecule. So, what I made there is called a hydrogen bond. And I find that very confusing. I want you to note the difference between a hydrogen bond, which is just a type of intermolecular force, an attraction from one molecule to a different molecule. See how that's so different from the covalent bond within the molecule. This is a bond to hydrogen. This is a hydrogen bond. Clear on the difference? Hydrogen bond is just an intermolecular force. So hydrogen bonds, because the charge is greater on that little tiny hydrogen, the charge density, it makes a really strong dipole-dipole interaction, which affects, again, the physical properties of the molecules. So let's get some data. I don't want you accepting just authoritative knowledge. That top molecule is ethanol. That's the booze molecule, and I don't care if you remember that. But its boiling point is 79 degrees Celsius. The lower molecule has the same molecular formula, but the structure is different. And it has a much lower boiling point, negative 25 degrees Celsius. Let's see if we can explain that in terms of intermolecular forces. If I looked at the realistic shape in a kind of condensed form, ethanol is a bent molecule, so it's polar. So it would be attracted to another ethanol molecule. The negative end of this one would be attracted to the positive end of this one. But not only does it have attraction between polar molecules, it has that specially strong dipole-dipole interaction called a hydrogen bond, because I have a hydrogen bond to a very electronegative oxygen, and that's attracted to the oxygen on the other atom. Hydrogen bonds are anomalously strong dipole-dipole forces, so it would take a lot of energy to pull those ethanol molecules further from each other into the gas phase. In other words, to boil it. It's got a high boiling point. Now, what about that lower molecule? I'm not going to flesh out the carbon-hydrogen bond because they're essentially nonpolar. But this is a polar molecule because it's bent, and it will have an attraction to another molecule. We've got a dipole-dipole interaction as the major intermolecular force here. Although there are hydrogens in that molecule, it can't hydrogen bond because the hydrogen is bonded to carbon, and that bond is essentially nonpolar. So looking at the dominant intermolecular force in both, I see that the dipole-dipole interaction in the lower molecule is weaker than the hydrogen bond in the upper molecule. Weaker intermolecular forces, less energy required to pull one away from the other into the gas phase. Easier to do that, lower boiling point. Do you buy it so far? Okay, wait, maybe I'm still putting one over on you. Because even within the category of dipole-dipole interactions, I said there was a continuum of strength. If the ethanol on the top was more polar, maybe it just has a stronger dipole-dipole interaction, and I don't have to call on this special intermolecular force called hydrogen bonding. Well, I've got some data for you on that too. On this graph, I can see the boiling point of different compounds as a function of what group of the periodic table that they're in. So, as I go across the first period of the periodic table, I take oxygen, nitrogen, and fluorine. That's going across. No smooth trend there. As I go down the periodic table, though, which is what I meant the first time, oxygen with hydrogen on it, sulfur with hydrogen on it, selenium with hydrogen on it, tellurium with hydrogen on it. Look, other than water, the boiling points follow a nice smooth trend. It looks like water has an anomalously strong intermolecular forces, which give it an anomalously high boiling point. So there must be something special going on when I have a hydrogen bonded to oxygen or to nitrogen or to fluorine, because they have boiling points that are outside the trends of the other members of their groups. Methane has a boiling point down there. No hydrogen bonding. So we believe in hydrogen bonding. It's really significant. Of course, I don't have to convince the biologists of that. If you've studied DNA, then you know the importance of hydrogen bonding in life. I've shown on the left-hand side the 2 strands of the double helix. Now, I'm no biochemist, but my understanding is that if you want to duplicate your DNA, you have to unzip that DNA molecule, separate the 2 strands so that it can be copied, and then let it pair back up again. So what we want between those 2 strands is an attraction of intermediate strength. If those 2 strands were connected by covalent bonds, you'd never get them apart. That's way too strong. What does attract them is hydrogen bonds. So on the right-hand side, we have a picture of the actual molecular structure of the 2 strands. There's the backbone of the DNA, and here are the different base pairs that you have, say thymine and adenine. The NH here, that's a hydrogen bonded to a very electronegative nitrogen, makes a strong hydrogen bond attracting it to the nitrogen in adenine. And similarly, NH attracted to an oxygen. So what holds DNA together are a group of hydrogen bonds, just strong enough to hold it together when we want it to, but weak enough to overcome when we want to replicate the DNA. By the way, if you wondered why A always goes with T and C always goes with G, it's because the shapes of those molecules are exactly right to let the groups that want a hydrogen bond together be close enough to do that. Nature is astounding. So DNA is one good example of the importance of hydrogen bonding. Water is my favorite chemical because extensive hydrogen bonding in water makes it very unusual. What I can see for these water molecules, they don't make a single hydrogen bond. The oxygen here can make a hydrogen bond to the hydrogen on this adjacent atom, but also this hydrogen can make a hydrogen bond to that one, and so on and so on. So each water molecule can actually make 4 hydrogen bonds to other molecules. And that's why the boiling point of water was so much higher than those other compounds I showed you on the graph. Water molecules are held really tightly together, and that shows up in a number of factors. One is the boiling point, but let me show you some other physical properties of water that are affected by hydrogen bonding. This is a picture of a water strider bug sitting on top of water. And why doesn't it just fall through? Because when I look at the individual water molecules, where's my pen? There it is. There are attractions, these strong hydrogen bonds, holding one close to another. The bug is light enough that it's not pressing down hard enough to overcome the hydrogen bonding between the hydrogen molecules, and the bug stays on the surface. Water is the most unusual chemical. It is the only substance I know where the solid is less dense than the liquid form. Usually in a solid, the particles are packed together tightly, which makes it more dense. But for water, the liquid can pack together more densely than the solid can. That's because in the regularly highly ordered solid, the crystalline form, one water molecule locks in a hydrogen bond to all the other ones. And the angle that happens at is determined by the bond angle in the water. That leaves empty spaces in the center. Increased volume where the mass stays the same. So the density of the solid is less, and ice cubes float in water. I can't think of any other liquid that does that. Another cool thing about this is that snowflakes, you can see now, have 6 sides to them. They're hexagons. And why is that true on the macroscopic level? Because at the microscopic level, the water molecules pack together to make hexagons. Again, now you're getting the payoff for your patients in studying chemistry. We're explaining the real macroscopic world by looking at the microscopic properties. One last slide to tell you about water. This is to show you, again, the density of water at different temperatures. And below 0 degrees Celsius, the density of ice is lower. When it melts to become liquid, the density increases. Another thing that you can see here, which is not my main point, but interesting anyway, that you can see that the density of water and ice are not constant. They depend on the temperature. The density of liquid water above 0 degrees Celsius actually is at a maximum at 4 degrees Celsius. So that's, on this graph, is kilogram per cubic meter. That's the same as 1 gram per cubic centimeter, or 1 gram per milliliter. Now, that's on that axis 1.000 and 0.9999. So if you want to use the density of water to only 3 significant figures, it's 1.0 grams per milliliter for all the temperatures that we would ever be looking at. All right, friends. So we've looked at ion-ion interactions, full charge with full charge, ion-dipole, full charge with partial charge, dipole-dipole, partial charge with partial charge, and the special case of hydrogen bonding. When I come back in the next video, I will talk about weaker intermolecular forces.